Welcome is this working? Yes. Okay, welcome everyone. Thank you for coming this afternoon. And thanks so many of you for being punctual. We hope that you don't feel dishonored by the fact that we're starting 5 minutes after, but we just thought we'd give it a few minutes to go. So yeah, thank you so much for being here. I'm Mark Kennedy.
I'm Ken Benoit.
He's from the LSE.
He's from Imperial.
And we're teaming up together, as we did last year, again, to do this DSI squared. By the way, we're both from data science institutes at our respective institutions, directing them in each place, which basically means trying to keep up with everybody. So today is a generative AI symposium that has a theme around trying to figure out how we sort of manage it. Today, here at Imperial, we're going to talk about some of the more technical aspects of that, as is kind of our natural division of labor, but not exclusively. And then tomorrow...
So tomorrow, we're going to be doing the same sort of format, but at London School of Economics, same sort of timings. We've got 3 panels tomorrow. We've got one on healthcare, we've got one on sustainability, and one on how AI is changing education, followed by a keynote speaker from DeepMind, who will be doing a fireside chat format with me, talking about how AI for science is driving progress, and hearing what's going on at a place like DeepMind.
So it should not be dull. There will be sort of conversation points as part of every session. So we'll come to the end of the remarks, we'll do a little chatting with the speaker, we'll open it up so that you can participate. What we have found is that for this kind of a format and for this topic, it's very helpful to open it up and have a conversation. We will do our best to manage the conversation if it needs it. So we'll just be trying to include everyone. Don't feel offended if we move it along a little bit at some point. Did you have something to add? Okay, cool. In that case, let me talk about today's agenda in a bit more detail. So coming here today at Imperial, thank you, Ken, is we're going to start with the state of AI. And my colleague, Dr. Ovidiu Serban, is going to chair that. And we have presentations from Rossella Arcucci, from Wenjia, and also from a longtime friend of mine. We both went to undergraduate back in the day, back in California, Ron Chrisley from Sussex. And we're really just talking about, okay, where are we now? You know, there'll probably be a little bit of how did we get here, but it's, you know, just trying to get a sense of where the cutting edge is at the moment. Then there's thinking about, okay, given that we have all these new capabilities that we haven't really seen before, what do we now know about the kinds of things that we need to do to make sure that when these get deployed, that we can trust them, that's being done responsibly. So that's the second session. My colleague, Dr. Kaison, is going to chair that one with Shakil Khan from Validate AI and Professor David Schreier here from Imperial. Session 3 is about accountability and transparency. And this is my colleague, Yves-Alexandre Desmourgeois, and he is an expert worldwide in all kinds of computational privacy, runs a computational privacy group here at Imperial and at the Data Science Institute. Session 4, looking ahead. And then Ken is kindly going to moderate that for us, and that's 3 of our panelists who you can see and whom I just talked about. So that's the arc of the main part of the afternoon. Then we'll have a break, and then we have a keynote this evening, which is Dr. Laura Gilbert from the Incubator for AI. I.AI is the cool name for that, by the way, just so you know, at the Cabinet Office in number 10, and she is going to give us her view of what's going on, and then there's drinks after. So that's the plan. And I thought in order to sort of get us a little bit loosened up for this, I would give you a highly technical quiz. It's not highly technical, it's not a quiz, okay? So that would be mean. I can be mean, but I'm not going to do that today. So what are we feeling is really where I want us to sort of start. Are we feeling like that? Call it out. This is audience participation time. What is she feeling? What word would you put to it? excited, yeah, like, okay, this looks pretty cool. It's on, let's do it. I have felt like that. I have to say that. I have felt like that. Or maybe we're feeling like this. What would that one be? Pensive, I like that. That's just the word I would put to it. He's really still thinking this one through. Okay, what about that one? Yes, at least anxious, okay? Maybe fearful, alarmed, some of those things like that. Maybe we're feeling this one. Distressed? Pardon? Confused? Worried? Untrusting, yeah. This is with our assurance theme. This is perhaps the look where you're like, I'm not so sure about all this. I don't know about these characters. Are they real even? How about this one? This is writing the PhD. Yes, okay, so there are many words that could, and I've by the way, I think I've felt all of these. How about that one? Disappointed, I think, yeah, that definitely could work. Sad. To me, this is the kind of look that I would give to my kids at a certain age, to say, I'm a little disappointed, just to let them know that I think it could be better and that this was serious, but they actually weren't in deep, deep trouble. How about this one? Yes, confused, overwhelmed. This is making my head hurt. If you haven't felt this one yet, you're either much smarter than me or you haven't been thinking about this very much. This is something that does come as we engage these topics. Pardon? It looks like a toothache. Okay, it could also be a toothache. Or maybe somebody's just hit him really hard in the jaw. That's possible too. Yes, he's trying to manage a Zoom call or Teams or something like that. Somebody's just said, you're on mute. All right, maybe this one? Yes. I think this is also, there's so many ones that you could go with this. This could also be the tech bro, why is everybody so stupid? It could be like, I'm so bored of this. Everybody's talking about AI all the time. Can we please stop? So I think that will happen if it hasn't. Or what about this one? Confident, content, optimistic. This is the kind of person I would like, this sort of affect. I would like this in my boss managing through this. I think she is projecting, we got this. It's going to be okay, And I can't tell you that is an automatic, but I can tell you that this is something that we can together achieve. If we take all of these range of emotions seriously and work on the range of things that we need to confront and deal with in order for this stuff to happen positively. And that's really what we're going to be talking about over the next couple of days. And if we get to that place, I hope that we can actually be a little bit like this last one, which is my favorite one. This is the one that got me to want to be an academic in the first place. Also probably is the one that got me, into, as my first job after university, working in a startup. It's just wonderment, just amazement. The joy of discovery, the pondering of what might be, and thinking that you could actually recapture that feeling of being a kid and thinking so much is possible. So that's what we're here to do today and tomorrow. We're excited that you're with us. Thank you very much. And with that, I'm going to turn it over, and I should have this all memorized, to Ovidiu. Over to you. Are you ready? Okay.
Well, I don't need that.
Okay.
Perfect. Okay, well, I may need this clicker. Okay. Well, welcome everyone. It's my pleasure to chair the first session on the state of AI. It's very, very hard to follow Mark's introduction, but I will try to have the same level of engagement and excitement. So we, as an AI community, we've been talking a lot about generative models lately, large language models in particular. But we often forget that artificial intelligence as a field is much older than this. In fact, generative models and large language models are a relatively young technology compared to everything else. So even though my students don't believe this, I'm actually much younger than AI as a field. And I still did, in my undergrad, I had lectures on symbolic AI and expert systems, if you can believe, and nobody talks about this anymore. So with generative models, and with large language models in particular, we often forget that this started in about 2013 with the development of word vectors as a technology, which was one of the foundational models that was developed for by the natural language processing community. So Thomas Mikolov and his team published the famous Word2Vec paper in 2013. And then in 2017, we had Attention is All You Need, which is one of the foundational papers that introduced the transformers concept. And then everything started from there. So as you can see from this evolutionary tree of large language models, after 2018, we had a very, very vast number of models that were developed at a very, very fast pace. Models that are fashionable this week are no longer going to be fashionable next week. And people often forget about them because there is another one who has higher performance and higher accuracy. There is also an environment with closed and open source models, as you can see here, and there is a lot of competitions from all these communities. I personally don't believe we are at a place where we can ask generative models and large language models to solve very, very complex problems yet. But I'm very, very hopeful and excited that with LLMs, some of them are very, very good at putting my very messy thoughts into a very coherent set of sentences that I can present in front of other humans. And in fact, some of this speech today was actually co-generated with ChatGPT. So I had a very, very messy script. ChatGPT made it a bit better for me. And this image in particular was also generated by DALL-E, which represent the future council of LLMs, looking helpful and confused at the same time. So I also imagined a scenario where we could ask LLMs to rank and discuss very, very important topics. So I asked 6 large language models, what are the most influential AI technologies developed in the past 10 years? So as you can see, some of them were very, very consistent across the different options. To my surprise, only a couple enumerated LLMs and transformers as the most impactful technologies, even though all the LLMs that you see on the screens, both closed source and open source, are based on LLMs or on transformers, and LLMs are as foundation. And then I also asked, what should we focus on next as an AI community? What should be our priorities? And to my surprise, they were also very, very focused on explainable AI and AI ethics. And we do have a couple of sessions today and tomorrow focusing on this at this conference. And we also see that there are some emergent fields that have been identified by the AI and the LLM models. Okay, so enough about introductions and enough about large language models. Today we are going to see in this first session, we're going to see 3 presentations. First is going to be Dr. Wenjia talking about learning generative models about health and using AI for population imaging. Then this is going to be followed by Dr. Rossella Arcucci and her journey into developing AI for climate mitigation and natural hazards. And then finally, we are going to have a presentation from Professor Chrisley about his experience in moving beyond LLMs and the challenges of deploying generative models in different contexts. So each speaker will have 15 minutes, and then we will have time at the end for a Q&A session. So hold your questions until the end. Well, thank you very much. Wenjia.
Thanks for inviting me to this talk. So my name is Wenjia. My research field is on machine learning for medical imaging. And today I'm going to talk about generative AI for population imaging. So we know that our human body is consisting of multiple different organs which are working in a coordinated way. And in the past maybe 10 years, my work has been focusing on the imaging for the heart, which is in the center of the human body, and perhaps one of the most important organs for our body. And the questions that I'm interested in are, how do we describe the shape and the motion of the heart, and how can we differentiate between a normal pattern of the heart from the abnormals? And this is not an easy question, because we know that first, this is a 3D geometry, which can consist of maybe thousands of pixels or thousands of points to describe its shape. Second, the heart is consistently moving, it's beating. So when we do not only need to describe its shape, but also want to understand whether it's moving in a normal manner. And if we look at some other biomarkers for our body, it's maybe relatively easier to analyze, such as blood pressure. Blood pressure is just a number. So I think majority of us know that what blood pressure is normal and what is hypertension, because we can simply set a threshold for this number. However, if we want to understand whether a 3D shape or even 4D shape and motion is normal or abnormal, it's non-trivial. And that is why that I dive into this field of generative AI, that I want to develop methods to understanding what is the normal pattern for the heart from a generative perspective. So generative model is like developed in the machine learning community to describe the distribution of high-dimensional data. By high-dimensional, it can mean like a very long paragraph. It can mean 2-dimensional or 3-dimensional images. And in my case, in my research, I look at the shape of the heart as a high-dimensional data. I want to use generative AI to describe the distribution of this high-dimensional data. And in this way, perhaps we can provide a reference model for the normal heart. For example, if we know for blood pressure, maybe your 80 mmHg is normal for your blood pressure. And similarly, for the heart, we can also define something to say, okay, this shape should be normal for the heart. And we can also use this generative model to understand what factors that each clinical factors or other environmental factors have influence on our heart. The reason that I'm interested in generative model is that it provides us a way to intervene with all sorts of factors. So generative model, you can imagine it takes some input, which are factors such as your age, your gender, or maybe your lifestyle, and then it can generate some data that describes you. And that means that it allows the scientists to do all kinds of intervention to see if we change something, how does it influence the impact? And in my case, I'm developing this blue block, which is generative AI model in the middle, which takes a number of clinical factors, including gender, age, weight, height, and blood pressure, and the output is a 3D plus temporal shape for the heart for this normal population if you have such age or gender. And to learn such a generative model, we need a lot of data sets. So we know that ChatGPT is trained on language data from the entire civilization. So it searches for all kinds of data on the internet from different countries, and then it's used to train a very capable model. And in our case, we're looking at medical imaging or healthcare data, which is not easy to acquire. And for this, we resort to some unique data resources that is collected in this country, in the UK, which is called the UK Biobank resource. The UK Biobank is a very large cohort of population for 500,000 people across the UK. So if you look at the geographic locations of where these people come from, it covers the entire UK geography from south to the north. And for each person, we get all kinds of information from them, including the lifestyle, some biomarkers, all kinds of physical measures about your weight, height, your blood, maybe biological samples from blood, saliva, etc. And most importantly, we also get the imaging data for a subset of this population. So we are acquiring imaging data of their heart for 100,000 subjects in the UK. And this will be the largest possible data set nowadays in the planet that you can access if we want to do research about medical imaging. And from the cardiac imagings in this data set, we can perform automated segmentation for different chambers of the heart using machine learning techniques such as CNN or transformer or other kind of approaches. And after segmentation, we can accurately describe the structure and motion for different parts of the heart. And the next question is, if we now have these segmentation maps for the cardiac structures for a large population, how do we build a model to describe what the normal pattern is? And we propose a framework, which is shown here, which may look a bit complicated, but the central idea is that we take this 3D plus temporal segmentation map of the heart as the input. We try to develop something called encoder, which is this blue block at the top panel. And this encoder can project this high-dimensional segmentation map into a very low-dimensional feature vector that describe its shape. And at the end, from this low-dimensional feature vector, which is also called a latent vector sometimes, we can add some maybe green blocks to reconstruct the original high-dimensional data, which is shown at the bottom. Because the heart is moving, we have another dimension, which is a temporal dimension. We also want to account for the information in that dimension, and for this aim, we incorporate something called a temporal module into this model to model the dynamics of the latent vector. And by dynamics, I mean that how this heart is beating across different time frames. And at the end, this model can describe how each heart is moving, and also for each heart, we can give it a latent representation, which means a vector to describe its shape and motion. And to elaborate for this temporal module, we're using a long short-term memory model, which is, in short, LSTM. And the input to STM is the latent vector at the first time frame. And this LSTM can learn the long-range dependencies between different time frames and try to reconstruct the latent vector at each time frames. At the end, when this model is built, we trained it using our existing segmentation maps acquired from the UK Biobank dataset. And we try to evaluate the performance of such generative model. For example, how does it perform for sequence completion tasks? And by sequence completion, what I mean is that we can provide the first time frame of the heart as input, which is this first figure at the top left. And then the model can give you some prediction how the heart is going to move for all the following time frames, which are all these shapes within this gray block. We can also perform sequence generation tasks. And for sequence generation, we no longer need any input about segmentation. The only input we need is some information about this human, about this person, such as if we know this is a female participant who is between 20 and 30 years old with certain weight, height, and with certain blood pressure. Then we can use this trained genetic model to generate the heart shapes at different time frames. And because for this population, there can be different people following in this population, there can be a distribution that spreads this population. The genetic model can also learn this distribution, and it can generate a number of samples to represent this subpopulation. So here you can see 6 columns, where the first column shows the heart shape for a real person in this subpopulation, and the last 5 columns shows 5 completely generated synthetic samples of heart shapes for this population. We can also use the genetic model to perform a study called simulated aging. Because for this genetic model, we have some input factors we can control, such as age, gender, weight, height, blood pressure, etc. We can freeze the majority of the input factor and just change one of the factors, such as age. And in this way, for any person, if we know what their heart looks like at 20 years old, we can change this factor of age to predict what their heart will look like in 10 years' time or 20 years' time if they don't have any disease, if they follow the trajectory in the normal population. And to quantitatively evaluate the performance of this simulated aging study, we draw some quantitative measures from the data samples we generated, and then we can plot these measures, such as the volume of the heart against different age. And the curve you see here are one clinical factors describing the heart against different age groups. And we have 2 different colors here, where the female group is represented using the blue color, and the male group is represented using the yellow color. And all these samples are generated by the model without any real data. And then we compare the trajectory we have found on this synthetic data set to the trajectory you can find in the real data set, which is shown at the bottom. So if you look closer about the slope of these curves, you can see that the slope of the simulated data is consistent with the slope in this real data. We also did a bit more quantitative evaluation. We can calculate the data distribution of all these numbers, and we can compare the distribution between the real data and the synthetic data, and there are some quantitative measures in machine learning that can tell us how close these 2 distributions are to each other, and we have found that this genetic model can perform a quite good job. Okay, so maybe that within this 15 minutes, I have shown you the state of the art of genetic model applied to medical imaging. And I'm only showing it for one purpose, which is to generate a reference model for the heart. But in medical imaging, genetic model can have other purposes. For some data sets where we have very limited training samples, we can use genetic model to generate more samples to improve the model training performance. And here in my work, I'm trying to demonstrate that the genetic model can generate synthetic but highly realistic samples to describe the heart shape and its motion. And also, all these numbers or quantitative phenotypes derived from the synthetic data are very close to the real data. And there is still some work in progress in my group, such as now we have this reference model to describe the heart for any populations. How can we use it to understand the deviation of any person or any person's heart away from this reference? So we train this genetic model only using normal healthy people's data. That means at the end, we can describe if you're 20 years old, if you're male, what a normal heart looks like for this group. However, if we have some data which are deviating from this reference model, would this mean this can be a risk factor for some certain diseases? Currently, we're still not quite sure about this, and we are currently conducting more experiments to explore this direction. The other direction I'm interested in is how can we move from a model describing the shape and the motion of the heart to a more comprehensive model describing the heart. We know that the heart is not only described by its shape, it also has a lot of underlying biological mechanism in the heart, such as the electrophysiology, or which means how the electrical waves are propagating on the heart, or some biophysics property of the heart. And I'm also collaborating with other researchers at Imperial College, Sheffield University, and Alan Turing Institute, and we're trying to build a more comprehensive model, which we call a digital heart model, a digital twin model, to describe different aspects of the heart. I'm sure that in the next maybe 5 years, there will be more research outcoming from this field. I'm very looking forward to explore this further. Thanks for your time and attention. So I'll hand this to the next speaker.
Thank you. Thank you very much. Microsoft. Somebody was saying before, yeah, you see? Yeah, this is the proof that your comment was like correct. So welcome, first of all, everybody, and thanks for being here. As Ovidiu was introducing me, I'm Rossella Arcucci from Imperial. And I work also in the Data Science Institute as Director of Research. And I'm part of an academic of the Department of Earth Science and Engineering. What I really want to talk about today is something called AI for Good. The reason why I will mention that, and let's say over the next 10 minutes I will focus on this topic, is that I'm also part of the World Meteorological Organization, which is one of the agencies of the United Nations. And the WMO, together with other agencies of the United Nations, is really working a lot on this topic of AI for good. Before proceeding, just wondering, do you know what is AI for good? Just few. So, before starting, as you know, going deep in the AI for good, then let's just have an idea. This is a YouTube video, so not sure about the quality, but let's see. Is it working? It's okay, sorry. So, this was just to give you an idea about what we are talking about. This is the AI for Good. The motivation why we are really interested in working on AI for Good is what we see when we look at the statistics. The number of people that every year we lose because of natural hazards. So I'm talking about flooding, I'm talking about cyclones, I'm talking about wildfires, I'm talking about also all the consequences of these natural hazards. It's not just the natural hazard itself, it's also what happens after to these populations. And if we don't want to look at the populations, then there is also an impact on the economy in general. So the key question, obviously from a data scientist, somebody working on the AI, is, okay, can we really do something? Can we develop models to help saving some of these people? So it's $1 million question, actually, because what can you really do to help? So the main two topics that we work on, just for that, is I usually, we separate them in two. The first is climate mitigation, for sure. If we try to mitigate a bit this climate change, so working on green energies, taking under control the emissions that we have, etc., then for sure we can have like an impact. Yes, but if you imagine, then we have this transition toward net zero, so we are trying to work a lot on green energies, etc., but this will take like a long time, right? The impact that you see is like long time. In the meantime, we have all these natural hazards happening anyway, and the number of them is increasing day by day, actually. The number of flooding that we can experience now is strongly higher than before, same for wildfires, etc. So we say, okay, let's work on act instead of react. So let's see if we can use AI also for natural hazards. However, when you try to work with the AI technologies, I have to say, as I often say, I'm a mathematician, so I can be really detailed and make you fall asleep in a couple of seconds. I will avoid that. So all my next slides will be very high level, no equations, and just what I would really like to have is more having questions in your hand after, more than giving you answers. So about the mitigation, green energy. Good. Let's say, can we do something? For example, we have a big project on waves energy converters, others on wind energies. But let's say wave energy converters. Can we really use AI for that? So let's say, in particular, can we use generative AI for modeling waves energy converters? The key question is not that, because actually, if you use generative AI and you generate, I don't know, images of people, for example, actually my question for Mark was, are these people artificially generated in your presentation? No, they are real. Okay, so, but if you have generative AI and then you generate photos of people, then you can see, okay, this looks real and not, right? But what about generative physics data? It's different, right? One point is generating a video when you see a wave or stuff like that, but having the inside that then there is a physics model behind, that the dynamic is realistic, that is actually what's happening in real world is another story, right? How can you use generative AI if then it's not producing meaningful data for you? So this is our main question. And we partially, we are answering these day by day. This is one of the work that I have with one of my collaborators of the data learning group. Essentially, using generative AI to produce physics data, and then, of course, you want to check if the data that you have produced are actually following the equations that you were imagining. Other applications, for sure. In the meantime, you are working on green energies, but also you want to understand what's going on in terms of the previous sources of energy, which are like a high source of emissions. So how can you really check if there are emissions in a country when the satellites are giving you images like on the left-hand side? So it's like you look at the image and you say, what's that? So then where is the source of the emission? So something that you can really do with artificial intelligence, and there is this is another work with one of my PhD students, is using AI to increase the resolution of the images so that you can understand where is the source of emission and take a better map of what's going on in terms of quantification, also for the sustainability, for the Sustainable Development Goals, and all the information that we have about the annual emissions at the country level. Other applications, of course, I was mentioning natural hazards. And in terms of natural hazards, I want to mention two, essentially, wildfires and flooding. The reason why we usually, I like to mention both, is that they are two natural hazards, but they are completely different. So wildfires are actually unpredictable until it started. So you can have a risk map and say, yeah, this area is dangerous, etc. But until it started, you cannot really predict a wildfire. Flooding is completely different, because flooding with the weather data, you can understand what's going on, and maybe you can predict that. So there are two, from the data perspective and the type of analysis and prediction that you want to make, they are completely different, right? So let's talk about the wildfire first. As I said, until you have to wait that it started to make the prediction. So how you can really understand if a wildfire is starting? Of course, you can analyze the satellite data, but by the time the satellite is moving and then sending you the image, and then you analyze that, then it's like, it's taking at least 6 hours. So in the meantime, if you look at the analysis of the type of interaction that we have with social media, do you use social media? Come on. Even if you are not posting, you are checking at least once per week. So luckily, in our case, because actually we were checking all these numbers and feeling, oh, can we use this for good? And so we came out with this point of having then data from humans for good, and we call that human sensors. So essentially, when you post something and it's related to a climate application, maybe somebody is using that for good. We use that for detection in real time of wildfires. So the system works like this, essentially. You post something. Our main test cases are usually in the US, California, and Australia. We can say that Twitter, now X, is still very popular. So people are still posting all the time what's going on. With the geolocation, then you can understand where this person is. Of course, with a range of error, because if you are posting something about wildfire, hopefully you are not in the middle of the wildfire. If yes, you are running. If not, you are posting something, then we can get your geolocation, and also together combine that with the risk map, we can understand more or less what's going on, where, and then make simulations still using generative AI, but with physics meaning. So you have the coordinates. This is, for example, a test case. This is the Chimney wildfires, one of the very popular. We have plenty of them. I'm sharing the link, so in case you are interested, there are other works that we have shared here. So essentially, as you can see, it's not like the exact geolocation, but if you have an error of 1-2 kilometers, it's still very reasonable in this case. Then you can forecast what's going on. As I was saying, using generative AI, but with a physics meaning behind. Why we want to understand if a wildfire is happening? Essentially for few reasons. One of the reasons is helping companies working with the fire barriers. Have you seen an aircraft like that before? It's like when a wildfire is happening, they fly, they leave these chemicals essentially building a fire barrier so the wildfire cannot propagate in that direction. And what happened at the very beginning when we were working on that, they came and they said, you know, we need help with the fire barrier. How? And we were asking, how do you select the placement of the barriers? Oh, usually there is an expert of wildfires saying, I think you should fly there or fly there. So we said, nice, good. How can we really help? What you can do with AI is simulating then in real time all the possible scenarios, checking how the wildfire will propagate if you put the barrier here or there, and then decide, based on optimization problems, what is the best placement. That one, let's say, is on a local level, so a wildfire happening. But if you look at this image, actually, it's a bit scaring because it seems almost that the planet is burning. But it's always like that, so don't worry. The key point is that we cannot stop all the wildfires. So we don't have the facility, the power to do that. So what we can do is understanding which one are more dangerous of the others. And this is what we do. For example, we collaborate with the Met Office, and we build like a digital twin of a software called Jules Inferno, which is simulating the global wildfire risk, as I said, on a global scale. So as I was saying, wildfires is not only one. There are also other natural hazards like flooding, that if you have access to the good data, as in this case, then you can really predict what's going on and maybe avoid these types of situation, or at least have the situation but without the person there. So before closing, as one of the main aim of my research is also sharing and creating community, and because I strongly believe that only if you work in an interdisciplinary group and promote the multidisciplinarity of your research, then you can really do something for good. So in case you're interested, with our Data Science Institute and the Grantham, we created this virtual lab called Data and AI for Climate. And in Data and AI for Climate Lab, we also work on AI for good. So if you are interested, please engage. We are super happy to have you joining us. And so I just want to say thank you very much for listening. And I'm here the entire day until this evening in case of any question.
Very good one. Thanks. Hello, everyone. Thanks for your attention, and thanks to the directors of the Data Science Institutes for inviting me. I'd like to address directly the subtitle of this symposium, which is about making generative AI work well, and in particular, I want to focus on the effectiveness aspect, because that's something I've been engaged with recently, and the effectiveness of generative AI. And what's interesting is that, from my own experience, I can say that sometimes, at least, trying to get the generative AI to be effective means that you also can end up making it safer as well. So I would like to give you some examples of that. A little bit about my perspective. I'm in a strange transition period in my life in that normally I would say I'm an academic like a lot of you, but and here's a kind of boring history of that. But there's also this more recent pivot from academia to industry, and in particular to where a lot of the generative AI application to the real world is happening in Silicon Valley. But yeah, Mark already mentioned the first line there. That first row of that table is where I met Mark. So I guess probably I'm the person in this room who's known you longest, probably. So yeah, I initially had an interest in doing AI in industry, but then instead turned to academia and had a long career of looking at more theoretical aspects of AI, more philosophical aspects, also interested in cognitive science. But then more recently, but in 2018, not that recently, I decided that I wanted to apply some of these ideas to building stuff and having some kind of impact and shaping what I could see was about to happen in Silicon Valley. And so I co-founded this generative AI startup, and we're going strong, and we're growing, and we already have some stories. I already have some stories from that experience that I can tell you about making generative AI work effectively, at least in those under those constraints. Yeah, it's a bit of a mug's game. I mean, they say it's a mug's game trying to predict the future, but I think with the rate of change in Silicon Valley with generative AI right now, it's a mug's game even trying to state what the state of AI is. But I'll just attempt that and give you some impressions. Also, as far as what it's like, to give you an overall impression of what it's like launching a startup at this time, the entrepreneur extraordinaire Reid Hoffman is often quoted as saying that launching a startup, a tech startup in Silicon Valley, is like jumping off a cliff and building an airplane on the way down. That's what he's been saying for years. But I know him personally, and I've told him that I've had to update his story there, or his analogy, by saying that if you're launching a tech startup in AI in Silicon Valley now, it's like jumping off a cliff and inventing the airplane on the way down. That's really what it feels like. Let's see if I can advance the slide. Yeah. So the title summarizes at least one key takeaway, that for many or most use cases in the area that Tenyx is concerned with, LLMs are not enough, or at least off-the-shelf LLMs are not enough. Well, what's the use case that we're concerned with? We're a voice-based generative AI startup, so conversational AI, but not text necessarily, but voice. And if you want to do that, if you want to have a voice-based AI system, then just thinking that, well, what I'll do is I'll hook an ASR, automatic speech recognition system, up to the front of my LLM, and then I'll have the output go to some text-to-speech, and then I'm done, right? That idea is, as you might expect, very naive and ignores all the hard work. I'm sure you know very well about the problems of LLMs hallucinating. So if you want to have an effect, let's say your conversational AI system is going to take room bookings for a hotel. Then you can't have the model just hallucinating and say, yes, there's a room available, when there isn't, right? So you have to solve the hallucination problem from the outset. But there's also back-end integration. That is, when your agent says, okay, I've booked that for you, it actually has to make sure a booking has occurred. So these are kind of obvious points to make. However, there's also, you need some way of controlling your agent so that it respects the business logic. You know, what rooms are available with certain other features, or when do you upsell, or when are certain blackout dates, or there are all kinds of restrictions. And even the conversational flow, the order in which you ask certain questions, has to be constrained, and that's not going to be done just by using an off-the-shelf LLM. And it also isn't just a matter of prompting the model, putting in the prompt the kind of rules of your business. We know from hard experience that LLMs don't always follow those constraints. And also, since it's a voice-based application that we're concerned with, you can't just take, LLMs were trained on text data. the ones that, the most popular ones, the famous ones, the big ones. And spoken speech is very different from written speech. So if you want a good voice-based generative AI system, you're going to have to somehow address those problems of the LLMs that are available not being really designed for voice. And that includes things like what we call endpointing, which is when does your agent start speaking? Has the user, has the customer, has the human finished their thought, or are they merely pausing to think of the rest of their membership number, or what? So you have to have a predictive model there just to figure out whether or not your agent should say something now. And if the agent makes a mistake, you have to repair the conversation. If it turns out the customer wasn't finished and you interrupted them, you have to know whether or not the customer is now attempting to repeat that information, et cetera, et cetera. So there are a lot of details here that you don't have when just with a simple chat-based system where there's a send or a carriage return or whatever, some informal indicator that my turn is over, now it's your turn. But more importantly, and related to how I want to spend the rest of my time, there's the issue of domain specificity. So usually, in the case of a conversational agent, you have a particular domain in mind. I mentioned, for instance, hotel room booking. You're a particular hotel chain, and you want to have an automated agent, say, that can take room bookings. Well, you have a particular way of referring to your rooms. You have a particular branding, a particular jargon that you use. Off-the-shelf LLM is not going to speak the way that you've trained your human agents to speak. And again, it isn't necessarily solvable just by putting it in the prompt. So fine-tuning is still updating the model to reflect the particularities of your domain is something that still needs to be done in general. Now, everything I'm saying is, again, we're in a moving situation, so it could very well be that model is released tomorrow that eliminates the need for fine-tuning. But as things stand now, fine-tuning is very much a requirement of releasing effective generative AI models. Okay. So there's this fine-tuning. It takes time, maybe a little bit of money, but we can make generative AI effective by all these techniques, including fine-tuning, right? Well, actually, as you might not be surprised to find, fine-tuning itself has its own problems. So the main problem I want to discuss today is that fine-tuning a model can cause, this has been known for decades, for a long time, since we've had machine learning systems and neural networks, that if you train a neural network and then give it some new data, it can learn the new data, but then it will forget the old data. Here's some examples. These are actual examples from when it says pre-trained OPT, that's a particular model released by Meta. So when here's an example. If you say to the model, this is a conversation between a human and intelligent AI assistant, and the human says, what sport does LeBron James play? The pre-trained model gets it right. The correct answer is basketball. But once you fine-tune this model on some new data, like you want some in the domain that of application that you have, it gives this, the top 5 fine-tuning methods now will yield a model that gives this bizarre typographical slash as an answer. But the reason why we've collected these responses together, we have developed a fine-tuning system that still allows the correct answer, so you don't have catastrophic forgetting. So that basically, what I'm trying to say here is that normally fine-tuning causes catastrophic forgetting, but there are ways of dealing with this, and Tenyx in particular has come up with some fine-tuning methods that don't result in catastrophic forgetting. And there are a couple other examples here. These are examples of where the normal fine-tuning methods would yield, in the middle column, yield some loss of memory. You could say these models have forgotten the correct answer. But using our method of fine-tuning, you actually are able to retain the knowledge while still learning the new data. Another example is not about knowledge, but about reasoning. So these are examples where the model has to reason from some given information. It doesn't just recall something, but has to use the information in the prompt in order to infer something. There's an example here. Steve's job is dangerous. Steve can be called into action at any given time. Steve has to drive a red truck when he works. It can get very hot at Steve's job. Steve is well, firefighter is the correct answer. Normal, the best fine-tuning options other than ours would yield, for example, if you were training on hotel data, it would instead give a hotel-related response. And yet our method keeps the performance. So that's just a case study there of how one of the challenges in making these models effective is fighting this catastrophic forgetting problem, and it's something we have been able to overcome. So learning without forgetting has the benefits of, well, it has to be parameter efficient. So if you are going to fine-tune these models, you can't, it can't be something that requires months and months of training time or millions of dollars to train. You need it to be parameter efficient. And one of the side effects that, of solving this problem of not having catastrophic forgetting when you fine-tune is that you're able to preserve the safety of these models. You might know that a lot of the big models have been trained to be non-toxic and to not, for instance, tell people how to build atomic weapons by using reinforcement learning with human feedback. So humans have looked at the outputs of these models and indicated when a model output was not safe, and so the models become safer. Well, if you have catastrophic forgetting fine-tuning, then those safety guardrails are undermined, and the agent, the conversational agent, will actually go back to being toxic and go back to being unsafe. So that one of the benefits of getting the effectiveness right is that you maintain the safety. Our method doesn't undermine the safety guardrails. And because you can modify without forgetting, you can enable something called continual learning. So I don't have time to go through these charts, but they summarize what I've been saying in three charts here. Here's the safety. If you look at the safety before fine-tuning and after fine-tuning, there are these three different standard fine-tuning methods. They all reduce safety dramatically, but in our case, safety is only reduced a little bit. And also this chart is about forgetting. The other methods, you get a lot of forgetting, whereas our method, you don't. On the far right, you don't get much forgetting. And also, the point is that nevertheless you get those, but you do learn the new data. So fine-tuning is being trained on new data. You don't undermine the safety, you don't forget things, but do you learn the new data? Well, we show that yes, with our method, you do learn, even though you haven't lost the safety and you haven't lost the knowledge. So finally, the last thing I want to say is that this kind of method has allowed us to move away from proprietary models like the big, OpenAI, Google, Meta models, to open source models. We're able to take our efficient fine-tuning method that has the features that I mentioned before, and instead apply them to open source models to fine-tune those open source models so that they're as good as now the best proprietary models. And that has all kinds of great benefits, now economic, political benefits, like opening up innovation to smaller players, lowering the running costs, lowering the barriers to entry in entrepreneurship. And again, that's made possible by this continual learning method. So here's our our fine-tuned model, we fine-tuned Llama 3, which is an open source model, and we've got it so that it's better than one of the GPT-4 models. So for the first time, you have an open source model better on a raft of benchmarks. I'm not saying just one benchmark, but a whole suite of machine learning benchmarks. It's better than a GPT-4 model. Wait, there was another, and there's the leaderboard. So you can see that our open source model is up there with, it's better than GPT-4 0314, for example, even though it's open sourced and available for anyone to use. So finally, there'll be there's some issues about the future that I'd like to talk about maybe in the panel in the afternoon, about data pollution, about models that can employ true imagistic reasoning, and even models that break the trend of focusing on the statistical norm and generating according to the statistical norm, and instead generating something that maybe violates the statistical norm, even though it's informed by it. So with that, I thank you again for your attention.
Thank you very much. Thank you for all the nice presentations. So we have about 5 minutes for questions. And I guess we can also circulate a microphone. So when you ask the question, if you have one of the speakers in particular in mind, please ask that. Yes. So there's a question here.
Okay, it's me. Okay, my name is Stefano Bonfa, and the question is related both to the speaker, the last one especially for the climatological satellite initiative. And the question is, are you, let's say, familiar with the concept of European Union initiative on space data? That's exactly what they try to do. They try to, let's say, build an European, let's say, space data platform where you can do research on this space data. Now, this is a general question. Regarding the, let's say, the concept of generative AI and application using data, space data, we are involved in a project, it's called, especially on agriculture, on agri-food, on climate, and impact of, let's say, with generative AI on the real world of agriculture. It's experimental, let's say, initiative. It's an horizontal Europe research project that we apply. And the question is regarding how you can combine, let's say, the space data, the real data, with the, let's say, data comes from space in a way that we have to solve not in silos, but in a more comprehensive way. This means because we are talking about to see the impact and solving the problem, like climate, for example. If we do not consider climate as a part of an ecosystem, this means how you solve, how they will help you. This is the question. The second question is regarding, let's say, the error of this generative AI, especially on the second speaker, that make to you.
Okay, thank you.
Very much for your questions. Actually, if I can quickly answer the first question about the platform with satellite data, for sure we are also contributing to that. One of the key issues is that satellites are not coming with same types of data, same resolution, same alignment. So there is a lot of pre-process that people have to do to make sure that then the platforms are actually usable to scientists which are not experts of remote sensing data. So yes, absolutely, and I think actually we are really promoting this, so I think it will be really important. About the second questions, how to, if I understood that good question, you are talking about generative AI in considering also the entire ecosystem, like climate variables, etc. Yeah. So most of the models we are developing actually also include climate variables. It's not like we predict a flooding just considering, I don't know, rain. So there are lots of different variables, like from humidity, evaporation of the soil, like, you know, we are also considering these types of variables. And actually the aim is having an impact. So providing these tools to end users and decision makers. So absolutely these, so the entire ecosystem is considered for sure.
Okay.
Oh, my question is directed towards the first speaker. Listen, so what the speaker did was to compare the AI-generated images against digital knowledge. Mm-hmm. But as far as heart, shape of heart and other information is concerned, years of anatomical knowledge based on dissection has been built up. And so has he tried to compare what is found by AI with the actual knowledge in anatomy book? Does it contradict it? Does it, rather than just what is based in digital?
Okay, so Wenjia?
My understanding is that you are wondering, like, how do we compare the generated cardiac anatomy to the real cardiac anatomy? Is that correct? Yeah, yes. So there are different ways. If they are, because they are both 3D geometry, we can have some quantitative metrics such as dice overlap metrics, Hausdorff distance, to measure the distance between these two pieces of data. And apart from this, we also can extract some clinical measures such as the volume for the left ventricle, the volume for the right ventricle, the ejection fraction for both ventricles, for both the synthetic data and for the real data, and then to compare the difference. So that's what we did.
My question was more general. Most of us, what we know in books on anatomy, you see, because they also consider some pathologies. It may not be obvious in real life. So it's what we know, what medical students are taught,
yeah, so,
rather than what we learn from.
So I guess your question is about, in medicine, we're more interested in the abnormal compared to the normals. So, or such as what the pathology would look like. Yeah, we also agree with that. So this is currently what our current work is trying to achieve. So now we have learned this distribution of normal data. We want to understand for different kinds of diseases for the heart, what kind of patterns do they deviate from these normal patterns. But I would say that's still a work in progress. So we are trying to do something and publish maybe in the next year.
Oh, so you're trying?
Yes.
So does it contradict, say, Gray's anatomy? What medical students are taught in their medical education?
Okay, so I guess your last bit is that about how does this kind of generative anatomy affect the medical education, how the medical students learn about anatomy. Yeah, so
I think we can okay. Continue the discussion offline, just to have time for one last quick question. So there is one last quick question just behind you.
A question for Professor Ron. My name's Saki from London School of Economics. We're currently looking at the benefits of generative AI in education, teaching students to code and leveraging or optimizing their learning process. I think one of the critiques is around reasoning, it being able to perform logical reasoning rather than predictive models. So you mentioned something about imaginative reasoning. I'm just a bit intrigued, and if you can kindly elaborate on what you see as a potential of AI models being able to reason effectively.
Yeah, that's of great interest to me. I think it's a great application area, and originally my co-founder and I wanted to work in education, but at that time at least we couldn't get the product market fit and the numbers and everything. But I think it's a great application area, and there is this problem of reasoning. I think people are working on that, but I think there's still an important work in addition to reasoning to modeling the learning subject. So I think these generative models would be very good at learning the state of estimating what it is that the user does and doesn't know, and being able to generate, for instance, educational material or problem sets or tasks that are right on the edge of what I call their subjective edge of chaos, right on the border of what they can understand, or their proximal zone of development, or whatever. So right on the edge of what they can already understand, that pushes them just enough that someone else might find easy, or someone else might find too hard. And I think that's one of the examples of what I was talking about at the end about future work, of not just having generative AI that finds what's statistically normal and producing more examples of that, but instead trying to find out, well, what's something that is actually not normal or that's considered complex given the current model, but isn't too complex. So it's in this sweet spot. I think that's a great area of application. I'd like to, happy to talk to you about it during the break.
Okay. Well, thank you very much. That concludes session 1.